I'm seeing nothing on the YouTube channel, by the way. Hello, everybody. And we're unmuted, but... Can we restart from the top if nothing's going to YouTube? Oh, geez. Oh, bad start. Hello, everybody. Welcome to All Space Considered. Sorry we had a little technical glitch there. These will still happen, despite the fact we've been streaming throughout a lot of COVID. We're still getting better at that, better at this each time we do, so we apologize for that. We'll post that whole video that we made another time. We might even rerun it at the end of the show, just for folks that wanted to see what that was all about. We will tell you what all that stuff you were seeing actually was. Well, welcome to All Space Considered. This is Griffith Observatory's first Friday event, of course. We are live, not from Griffith Observatory. We are live and remote. And I am Dr. David Reitzel. I'm the astronomical lecturer at Griffith Observatory. With me is Chris Butler, our acting artist in resident, our space artist. With me also is Patrick So. He is the programs manager, and I forget your exact title, Patrick. I always flub it, but basically he's co-managing program department with me. And of course, longtime All Space Considered. And with us tonight is Natalia Guerrero, who's with us from MIT, the Kavli Institute, and she's going to talk about the Tess mission. We're so excited to hear all about that as the second, well, really the last third of our show. So we're very excited to bring you our show tonight. I think you did get a chance to see the titles that were up there and what we're covering. So we're going to jump right in. And Patrick, why don't you tell us all about what's been going on with OSIRIS-REx and the mission to go collect some stuff off an asteroid.
Yeah, it is a curious name, OSIRIS-REx, but it's an amazing mission to a near-Earth asteroid called Bennu. This asteroid has this spacecraft has three missions, which is actually not three missions, but three phases of the mission. And that is, one is to survey the asteroid. The second is collect a sample of the asteroid, and the third is to return that sample to Earth. So the collection is done by this collection arm here. It's at the end of the 11-foot kind of an arm there, rubber arm. And during the survey, there were four possible sites that the sample could be collected on from. So the one they decided was Nightingale, which is in the northern hemisphere of Bennu. And incidentally, Bennu is about the size of a skyscraper, so not a huge asteroid, but it is a small asteroid with a low surface gravity. This is how it was done. The OSIRIS-REx slowly moved down to the surface of the asteroid, and then the sampling collector, that cylindrical piece of equipment there, actually collected the material. Jets of nitrogen were blasted from that instrument, and then it only took about 5 to 10 seconds for that collection to take place, and OSIRIS-REx was on its way off the surface of Bennu. Now that's the animation, and here is the actual footage, several frames, looking right down at the arm and the sampling collector. And you can see it was a very very brief touch and go moment. And roughly about 60 grams of material was collected from this operation. And we recently got some pictures back from the site where the collection took place. This is what it looked like before. And here's a picture taken of it afterwards, and you can see there is a mark on the surface of Bennu left by the sampling collection. In this next image showing the same site, there is a boulder that's actually, a real boulder, about 1.2 meters across, that was dislodged from the sample collection. It's estimated that that boulder weighs about a ton. Imagine that.
Yeah.
So let's see. Now, for the final phase of the mission, in fact, starting next Monday, OSIRIS-REx will fire its rocket motors, and it will head back to Earth. But it won't be a straight beeline back to Earth, a straight path. It will be a long 2-year journey where it will basically circle the sun twice and then catch up to Earth. And when it does reach the vicinity of Earth, the sample return capsule will be released, and it will undergo its entry, descent, and landing phase. And then it will land in the Utah desert on September 24th, 2023, and where the sample will be collected and studied by NASA scientists and labs around the world. So that's the conclusion of that mission. It's going to be a wonderful thing, and it's heading back to Earth as of next Monday. So it's really great.
Well, super interesting, Patrick. To be getting that back, I'm going to be excited to see what that sample's like, because it's just jam-packed full of Bennu. We're going to have it delivered to our doorstep and be able to see what that rubble pile is actually made of, what it looks like. Even just the pictures to really show that some asteroids are big rubble piles was crazy, although we expected the pieces to be a little smaller. They had trouble finding good collection sites, I know. So anyway, a huge success, and it's on its way back. And now what's up with this? This looks like the Parker Solar Probe you're showing here.
Yes, indeed. So as Parker Solar Probe is designed to study the sun's atmosphere, which is called the corona, which means it has to fly very close to the sun and see what the environment is like. As close as, eventually it will fly as close as 4 million miles from the sun, and traveling at the fastest speed any spacecraft has traveled, roughly about 430,000 miles per hour, which is an incredible speed. Now, the Parker Solar Probe has an orbit. It takes it close to the sun, where it studies the sun's outer atmosphere, and then orbit that takes it just beyond the orbit of Venus, and that roughly is about a 3-month orbit. So on its way out, it's doing other things. And one thing it did was something it did last year, which was take a picture of the sky surrounding the sun. And on August 25th of 2019, it did that. Here's a simulation. It took a picture of Venus, Mercury, and excluding the sun, because it doesn't do that, because it'll burn out the sensors on the spacecraft, but also of the Earth. And when it did that, it actually found a curious thing, a band of light stretching from Venus, kind of centered near Venus, and stretching across the sky and going through the sun and off to the left, bottom left, which is out of this picture, to where the Earth is. Now, the picture it took actually looks like this through its wide field camera and near field camera. And what you see there is, with the labels there, you see Mercury, Venus, and this thing called a dust ring, which is kind of centered around Venus, and it runs straight through, and the sun is not visible. But on the other side, on the left there, with the dotted line, which indicates the band of what is called dust, you see the Earth. So what we're looking at here is the orbital dust ring of Venus, but we're seeing it edge on instead of kind of overhead. And this is the first time and the first picture taken of such a dust ring around in Venus's orbit. It's a 360-degree view image. And we've known the dust ring is there, but we've never had a complete picture of the true extent of that dust ring. So this is a very remarkable picture. And from that, we can kind of construct what that dust ring might look like around the planet Venus. Now, there is a great scientific debate as to the origin of these dust rings around the planets. And some scientists think it's from asteroids, some of them think it's from comet dust. And just recently, in fact, we did a story last month that Juno made some measurements and showed that there was a lot of dust from the planet Mars, and maybe that's the origin of a lot of dust that we see in the inner solar system. So it's an ongoing study, and the scientists will keep on studying, and we'll find out what is the real cause of these of the dusty rings around the planet's orbits.
Well, thank you, Patrick, for that. And speaking of dusty places, we've got a really dusty place in Mars. We just sent, of course, the Perseverance rover there. And you also see in this image the Ingenuity helicopter. But first, let's start with a little Perseverance news. The Perseverance rover has an experiment on board called MOXIE. And I love the name MOXIE for this. And what it's making is oxygen on Mars. It's actually the Mars Oxygen In Situ Resource Utilization Experiment on the rover. And it takes CO2, breathes it in, and breathes out oxygen. Kind of like a plant does, except it's that gold box doing it. Now, indeed, it did make oxygen on the surface of Mars. It made 5.37 grams total over the period of about an hour. You might think that that's not much. Well, that's enough to keep you alive for about 10 minutes. Okay, made it in an hour. I get that. So these numbers aren't good if you were really trying to breathe that. But the idea is you could bring a bigger one. This is, again, another one of those proof of concept experiments where they're showing, yeah, this works. We can actually convert it into oxygen and have something we could use to breathe and to, you know, again, you need oxygen if you're going to send people to Mars. So this experiment, another big success for Perseverance already. Now, what about that helicopter, Ingenuity? Now, right here, take a look at this. This, I believe, actually is the third flight. Second flight, it went up again a little higher, came down successful. Here you see the blade spinning over on the left-hand side of the image, and there it goes up into the sky. And then it's going to do a little tilt, and off she goes. And this makes a great background for Zoom, by the way. I'm not using it tonight because it's very distracting just to have a helicopter flying back and forth through one's head. But it's pretty easily editable where you can remove the JPL or NASA meatball at the end. And then it just loops. The helicopter's going to come back here in a second. That is not a still. This is still a video. It's not a still. It is a video that we're looking at. There's not much atmosphere on Mars. It's only about 1% of Earth's. So the fact that we're able to fly a helicopter, it uses blades a lot like a real helicopter where they turn the blades. They can do them either with the rotation, where they can do them at certain phases of it, or they can turn them all at once and give it more pitch. That's actually how it takes off, is by pitching those. They give it a surge of energy, it flies up into the air quickly, and then they can control and adjust the direction by pitching them different as the blades move around in the circle. So amazing that it flies like a real helicopter. This isn't like other things. Now, it gets shots to the ground as it flies around as well. There's its own shadow. Now, the blades look like they are frozen, but they're really not. It's just that the camera speed matches the speed of the blades as they spin around. So here's another shot of it, a longer one. And you'll notice the blades change direction ever so slightly as this video progresses. This is from the third flight, I believe, or maybe this is the fourth flight. Let me look over here, make sure I'm getting these straight. Anyway, it was a longer one, and you can tell that as the blades spin at this 2537 revolutions per minute, this camera is making, it makes basically 20 full rotations in between each image. So as we're seeing that ground pass below, and right now it looks like it only has one set of blades, but looks like a little dragonfly flying over Mars. We all quite like that. But there is a capability that has been unveiled here that a lot of folks didn't think about, but it's come live right now to All Space Considered in Griffith Observatory. And right here, we're going to explore it. We have the Mars traffic report. That's right. Every 10 Mars minutes now, with the eye in the sky, the Ingenuity Mars helicopter, we are able to pay attention and figure out what's up there. Let's check it out.
Well, it's 5 past the hour. Time to check traffic for your morning commute, and it looks like a real mess out in West Crater. Let's go to Ingenuity Chopper 1 for a live report.
Okay, here's the trouble, and it's a real mess. We got a rover that tried to get into some of the boulders out of the sulfate contact turnoff. And it looks like maybe a little excess speed. Oh boy, it tipped itself over right onto its side. We might have a plutonium fuel spill to deal with. This is definitely going to take some time to clear. In the meantime, I'd suggest you consider taking alternate routes if you're headed up onto the East Mesa. Back to you in the studio.
Well, things are looking interesting in Jezero Crater there. We'll have to check back on that wreck and find out what happened. Anyway, in all seriousness, of course, we're just joking that there was no wreck. Perseverance is doing just fine. There's not a problem at all. So don't worry.
Not a fuel spill.
No fuel spill. In fact, the fuel is quite safe. The plutonium is stored in a way that they believe that it could undergo a disaster upon launch, and those canisters would still be sealed and would be safe. They test them to those sorts of energies. They crash them. Well, they don't put plutonium in and crash them. They crash them with other substances and make sure they don't crack open. So they are very, very safe, but we thought it was a funny joke. But Ingenuity is getting shots from the air, and you can see those rover tracks down there. So it made us laugh to think, indeed, the rover is picking up signs that the helicopter's picking up signs that there's a rover down there. And in this next image, again, you'll see more rover tracks. And in this next image, if you look carefully, you see a rover right over there in the top left corner. Let's zoom in on this for you. So we thought it was quite funny. We had made up that joke about the rover crash and seeing it, and then JPL gave us this image with the rover up there. No, it's not on its side. It's doing just fine. Percy's doing well. Well, there's the landing site. This is about 80 meters away where the rover was observing these helicopter flights and the helicopter observing the rover. There's the zooming in on it. It's great to see Percy there hanging out, looking at the helicopters looking at Percy. So very fun.
Fantastic.
Now, these flights are not just for fun. They're, of course, measuring how well they can control a helicopter in that 1% atmosphere. Turns out this is the horizontal positioning, sort of left, right, and front, back. And notice it's mostly good to under 1/10 of a meter. So that's, about that far, 6 inches or so, give or take. Let's take a look at how the power is applied to it. So this is the rotor speed, essentially, the amount of watts they're putting to those the electric motor that turns the blades. So they spin them up, and then boom, you get takeoff, and then it can hover. And you notice they're not having to change the energy much at all. And that's the plan. Again, they change how the helicopter flies by changing the pitch of the blades. So this is exactly what they would hope to see during a flight, that it would be constant energy, more or less, no drops due to the battery or anything like that. Also, shots from the ground. Let me get to the next slide here. Shots from the ground, or of the ground from the helicopter. This is shortly after taking off, and they were thinking they might see a lot more dust than they did. And indeed, this is not very dusty at all, which is great for the helicopter because it's solar powered. It's not plutonium powered. It needs to recharge its batteries every day, and they are recharging. It's going well. In fact, it's going much better than they had hoped. Everything's progressing wonderfully. There is a little dust, however. This was an image, or rather a movie they took, and they enhanced it greatly, did some edge detection, and right there you see that dust kick up and get blown by the Martian wind. There is a little Martian wind that's there, but this is not much dust at all compared to a big dust storm on Mars. Now, this next flight, this was flight number 4. They got audio. Well, Percy, got audio of Ingenuity flying. Now, I don't hear a whole lot. Maybe it's because my ears are not so good. I'm going to be quiet here and let you listen to this. Turn up the sound. You can get this on the NASA website as well if you want to check it out on your own. But listen up. turns out, folks, that subwoofers help. The noise is very low. I'm playing it through my stereo that has a subwoofer, and now I can hear it. Very low rumble. Now the helicopter's coming back, everybody. Don't worry, we're not waiting around for nothing.
Didn't get stuck in a tree.
No.
There she is.
Yeah, there is a hum in there. Anyway, now it'll go away as she lands.
Fantastic.
Yeah, anyhow, impressive. I never thought I'd be hearing sounds from Mars. That atmosphere is so thin. It's shocking we're hearing it. Now, folks have made recordings of various music pieces where they pass them through computers, where they change the sound as they would expect it to be changed based upon the density and the composition of the various atmospheres. So go Google that and check it out. Maybe we'll bring that to you again. I think we did it once at an All Space Considered years ago. Anyway, to summarize and finish up this section here, on the right-hand side of this image is the third flight. On the left-hand side is the fourth flight. And the gray stuff you're seeing is the ground imagery that was taken during those flights that you can see. The first short bit we showed is the one on the right-hand side, and then the longer bit we showed with the blades where they were matching is the left-hand fourth flight. Now, they've got a fifth flight planned. This is very exciting. This is going to be the landing spot for the fifth flight. It's different. They're flying to a new location and they're going to land. Now, why would you want to do that? Well, notice Perseverance, of course, has wheels. So Percy's going to start rolling. They're not waiting around. They've got science to do. Well, if the helicopter wants to keep flying, they need to follow where the rover's going. They now have a plan, and they're flying their helicopter to keep up with the rover so they can keep doing more flights and having more fun. So I love it. I love this exploration. It's groundbreaking. And now they're into their next phase of the mission where they can kind of start being a little bit useful to the rover. And they're starting to get to be a little bit of doing some scouting almost. So a lot of fun, pushing it further and further. And now we wait to hear about things like Watson and Sherlock and wait to hear how results of those are going on. I read on Twitter that so far they're getting results and they're working, but they haven't detected anything that makes them say bingo, that this is great. So anyway, Bob, now Patrick, we're back to a story with you. We've got another PJ. So why don't you tell us what a PJ is and what it's got to do with Jupiter?
Okay, well, we're back to the Juno mission to Jupiter, which is, of course, its primary mission. And Juno has an orbit that takes us far from Jupiter and close to Jupiter. It's roughly about 53 days every its orbit. So when it's close to Jupiter, at its closest point, that's called a perijove. So we abbreviate it PJ, and it's number 33. This is the 33rd time that this spacecraft has made a close pass of Jupiter. And when these close passes take place, the instruments on board Juno are actually actively studying and measuring the environment of Jupiter. At its close pass, it's roughly about 2,600 miles above the cloud tops of Jupiter, closer than any spacecraft has gotten to this to the largest planet in our solar system. And from this, as it sails from the north to the South Pole, it takes spectacular pictures. And here are some of the latest images taken by Juno. This one is just right over the North Pole, roughly about 28,000 kilometers. And you can see that in these images, the North Pole looks very different from the banded regions closer to the equator. So these are really interesting images. And notice the bluish color too. All these images that I'm going to show you are color enhanced and are processed by the public. There is a program that you can take raw images and and enhance the colors in them and to make spectacular looking images like this. Here is a cyclonic swirly thing on Jupiter. But it's very interesting. I mean, I'm kind of swirly thing, yeah. But it's none of these have been scientifically kind of studied. That these images provide data for atmospheric scientists to figure out what's going on, and they're very, very intricate and detailed. Just basically looking at the storm and all the things are happening in this picture. So it's truly an amazing place, and this is just a tiny sample from a tiny portion of the surface of Jupiter that we're seeing really up close.
Oh,
this is this one is totally amazing. And remember, even though these images are formatted kind of circular, we're not looking at the entire surface or cloud tops of Jupiter. Yeah, exactly. We're looking at a very, very narrow field of view of it. And here we see on the kind of on the right there, a large folded filamentary region. And then there's a spectacular oval storm, which we'll see in detail in the next shot. And wow, I mean, it's almost like a piece of art. The high clouds are the kind of lighter looking clouds, which are made of ammonia ice crystals. And then lower down in the central region are clouds made of ammonia hydrosulfate, which is a kind of a reddish color. And here's a picture of the kind of north temperate region of Jupiter, kind of more closely to what you would see kind of in the banded portion of this world. And there's a detailed region. Those little white specks there are pop-up clouds made of ammonia ice above the normal grayish and reddish clouds.
Reminds me of a Van Gogh painting.
It is, and you can actually put it through filters and make it look like a Van Gogh too, if you wanted. If you want to see more pictures, because I didn't have time to, there were so many of them, you can actually log on to the Juno website. If you just type in Mission Juno, you get straight to it, and you can see many of these amazing pictures, not only from PJ33, but all the other missions before it. So there's amazing stuff in there, including the Jupiter's Great Red Spot. So there's a big resource there.
Well, thank you, Patrick. It's always, those images are always mind-blowing. Gorgeous, gorgeous shots from Juno. And I can't wait to learn more and more about the interior of Jupiter, too. It's probing the interior every time it flies close by, and we're going to learn more and more about what's going on in the insides of Jupiter as we get these gorgeous pictures of the outside. Now, between our last show and this show, we actually lost a great American, an astronaut that's really was one of our trailblazers. Oh, I'm skipping ahead too far. Is really one of our trailblazers, and we really felt we should honor him. And to join us tonight is Angelica Ruiz, one of our producers of the show, and she's going to tell you all about astronaut Michael Collins and his contributions, his life, and we're going to honor him. So thank you, Angelica, for putting this together and joining us tonight.
Thank you. Yes, I'm very happy to be here to honor Michael Collins. Passed away April 28th. This leaves Buzz Aldrin as the last living crew member of Apollo 11. To tell you a little bit about his life, he was actually born the same year as Neil Armstrong and Buzz Aldrin. He was born October 31st, 1930, in Rome, Italy, and there is actually a plaque in Rome celebrating the city as a place of his birth. The reason why he was born in Rome, he was born to a military family, and he actually traveled a lot during his youth because of that. He followed his family into the military, graduated from West Point in 1952, but he did not follow his father in the Army. He actually instead went to the Air Force, and he was a fighter pilot. He was a test pilot locally here in California at Edwards Air Force Base, and then he was selected as part of the third group of NASA astronauts in 1963. A little bit about his family. To whom we extend our condolences. He was married for a very long time to Patricia Mary Finnegan, over 50 years. She passed away in 2014. Had children Kate Ann and Michael, and Kate and Ann survived him. And that was a family that was waiting for him at home as well. He was on his missions. His first mission as a NASA astronaut was Gemini 10 with John Young. Very important mission. Actually it set records for altitude. It set records for rendezvous. The whole Gemini program was very important to prepare for the Apollo program, for which Collins was selected for, as the command module pilot for Apollo 11, making him actually the second in command of the crew. A couple of other things, contributions. He actually designed the patch and decided not to add the names of the crew to the patch because he just thought it wasn't that important. And he also named his ship Columbia. Let's go ahead and take a look at the launch.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Here we got a roll program.
So for those of you who may not know too much about the procedure of Apollo, as Neil and Buzz climbed into the lunar module to then descend onto the moon, it was Michael Collins' job to stay in the command module and orbit the moon alone. So he was in the Columbia alone and indeed lost contact, would lose contact with everyone, all humanity, while he was on the far side. There he is. This is a picture of Columbia taken from the Eagle. This was a very singular experience. He spoke about it. He wrote about it in his memoir, Catching the Fire, which he wrote in 1974. So to quote from him, if a count were taken, the score would be 3 billion plus 2 over on the other side of the moon, and 1 plus God only knows what else on this side. I feel this powerfully, not as fear or loneliness, but as awareness, anticipation, satisfaction, confidence, and almost exultation. Let's hear a little bit more about his experience in his own words.
This is in lunar orbit, showing the separation of the lunar module from the command module as viewed through my window. This was a busy time for me in that I was taking these motion pictures through the right-hand window. At the same time, I was taking still photos through the left-hand window, and also flying my vehicle and probably poorly, and taking a close look at the limb as he turned around.
I think that we were timely in accepting this mission of going to the moon. It might be timely at this point to think in many other areas of other missions that could be accomplished.
Everybody looking at me? I think long term, we find for the first time that man has the flexibility or the option of either walking this planet or some other planet, be it the moon or Mars or I don't know where. And I'm poorly equipped to evaluate where that may lead us to.
That was from the Apollo 11 post-mission press conference. You can see he was a man of extraordinary wit and a profound perspective. He was sort of done with his career as an astronaut. He declined command of Apollo 14. He felt that he had already had experienced so much that most human beings would never be able to experience. He did stay with NASA briefly as the Assistant Secretary of Public Affairs before becoming director of the National Air and Space Museum from 1971 to 1978. And there he is in front of the building. He oversaw construction of the new building of that institution. He was a man of very broad interests. He was a painter, a writer, obviously, a person very interested in words and language. And he was active in social media really up until his death. This was one of his last tweets on Earth Day. I am certain if everyone could see the Earth floating just outside their windows, every day would be Earth Day. There are a few things more fragile and more beautiful than Earth. Let's work together today and every day to protect our home. So that's me, Michael Collins. Thank you, Ad Astra.
Yeah. Well, thank you, Angelica.
Wonderful.
That was really wonderful, really lovely. And everybody think about Michael Collins and his contribution. It is amazing. He was offered Apollo 14 to go walk on the moon, and he turned it down, said, I've had my shot, I've had my chance. And there's not many people that would do that and let others have their chance and go walk on the moon. So you should remember him. So Chris, turning to you and more about rocket launches, but you've got a lot of memories about astronauts, don't you?
Yes, I do. Actually, I used to work on the space shuttle program before I worked with Griffith, but my father worked on the Apollo program. And so over the years, I've had lots of occasions to talk to the astronauts, even in more recent years. And you get to know them a bit. Now, I never had the chance to meet Mike Collins, but I always wanted to. And one of the reasons was when you would talk to the astronauts, sometimes you get lucky and they would tell stories about one another. And sometimes you get a juicy tidbit or two, but no one ever, not any of them, ever had anything bad to say about Mike Collins. He was universally liked. If he comes across that way in the press conference and so forth, as just being a humble, likable man who had good sense, that's exactly how he really was. And so I'm mourning not only an American hero, an explorer of space, a good pilot, all the rest of these things. It isn't just that for me. He was just a really good guy. So yeah, we're all going to miss Michael.
Great.
The future does go on, obviously, and we do want to talk about the space program and space programs actually, because we have a lot of international things to talk about. Let me jump ahead. Oh, there we go. With our out to launch. And things have been going on. We've had some interesting things go on. I want to give you an update or two. One of the things that you may remember from last time, I mentioned in some upcoming launches, a launch I did not have a date to give you or a time. We just knew it would be fairly soon. And that's because it was a secret mission. It was a National Reconnaissance Office launch out of Vandenberg in Central California. Well, it so happens that it may have been a spy mission, but we have our own spies, and one of our guides actually got up to the Central California coast when they announced it at the last minute and took a beautiful photograph of the Delta IV Heavy rocket, one of the biggest rockets in the world today. This on April 26th, David Pinsky got a beautiful view, and as I say, he's quite an asset to us, not only as a museum guide, but also obviously as an intrepid reporter capturing this secret mission on its way up. I'm especially glad he caught this because it was cloudy in that direction from Los Angeles. A couple of us tried to see it from here. We didn't get a look, but fortunately we had Dave to help us out. So thanks to David for that. Looking at other things going on, the Chinese have had a big launch here and some interesting follow-on to it. The Chinese are launching a space station, a big one. Now, they had a smaller experimental station they launched a couple years back, but now they're launching the beginning elements of a fairly large space station. They launched that on April 29th. It is successfully in space. I'll mention a little bit later, they're going to be doing both a cargo run to it, and then later some of their crew is going to go up and inhabit it for the first time. This was the core of the space station without anyone on board. It was delivered by a very large Long March 5B rocket and sent into space. Well, that's not the end of the story, though, because it turns out it's the rocket's coming back. Now, this is unusual. This is unusual. Normally, with a space launch like this, what'll happen is the first stage of a rocket will and it will fall into the ocean. And then a second stage will often be used to launch a payload the rest of the way into space. And these second stages do come back in and burn up in the atmosphere. But normally what is done is they're intentionally guided to fall into nobody home. The odds of being hit by anything falling down from space are very, very low. But normally the rockets come in a planned place. In this case, it was the big first stage that did all the lifting, no second stage, went straight into orbit itself. And it, for whatever reason, is not under guidance. It's actually tumbling end over end in Earth orbit. And in the next day or two, they're thinking Saturday or Sunday, it will lower its height enough to encounter the atmosphere, and it will burn up, and it will come in and go down to the surface of the Earth. Now, hopefully, that will be over the ocean. Hopefully, the Pacific, especially 3/4 of the Earth, is covered by ocean.
Chris, I'm going to interrupt here because your audio is coming in and out for some reason, and I'm not sure why.
It may be my internet connection, or maybe it's a plummeting Chinese rocket. No,
it could be a plummeting Chinese rocket causing you trouble, perhaps, but your video seems fine, which makes me not think it's your. It's that you might try muting your Zoom call or reconnecting to your microphone or something, and just see if that helps. But anyway, indeed, the story, just if anybody missed that, as Chris checks his audio setting, is they launched this part of a space station using the first stage, and the whole first stage did all the lifting, and they don't have any control over it. It's tumbling up there, and it's coming back, and we don't quite know when, but maybe this weekend, maybe sometime. Oh, Chris is seeming to reestablish his Zoom altogether. So, but very, very interesting stuff that we don't know when it's going to come. Now, don't worry too much about this. Yeah, chunks are going to hit the ground or the ocean. Most of the Earth is ocean, of course. People don't inhabit that much of the actual land. I was saying that on Twitter to a post that, I've hit a royal flush in Reno where I grew up. Okay, it was on a poker machine. It wasn't a big game or anything. I have a better chance of hitting another one of those the very next time I play than anybody being hit by any piece of this space junk. It's just not going to happen. So welcome back, Chris. Hopefully that fixed your connection. I was just telling folks that I have a better chance of hitting a royal flush on a machine in Reno the very next time I play than anybody does of being hit by this space junk.
We are quite safe. There's nothing to worry about.
Yeah. Well, I'm not sure you're any better, to be perfectly honest, but go ahead and carry on, and we'll see if that did help.
Let's see if the slides do a good enough job. We had the launch of Crew 2 on a SpaceX Dragon, which was very nice. That did mean we had a lot of people on the space station. We had 11 people, so that's almost a record. 12 is the most that have ever been there. They don't even have beds, so some of the people had to sleep in some of the spacecraft for a couple of days. That's fine. But then Crew 1, the first group of 4, they came home on a Dragon. This is a picture from the space station looking down at the actual reentry of the vehicle. So there they are, headed to Florida. You see the lights of Florida in the picture. And they splashed down in what was only our third nighttime splashdown. So the crew is home. All is well with that. Down in Texas, we had some excitement you may have heard about. All the testing of the giant Starship for SpaceX, their experimental rocket. I need to point out, nobody on board. These are technical tests. And I need to mention that because of some of the things you'll be seeing.
By the way, you're back, Chris, so everything's good.
Outstanding. Ladies and gentlemen, I'm back. If you have a look at the last 4 prototypes, ladies and gentlemen, yeah, I especially like the one all the way on the right. They launched in the fog. We didn't see it explode, but you saw the pieces falling. Very sad. But these are tests. They were every time they would go through one of these tests where they launched the rocket up, it would shut off its engines, glide back down like a skydiver, and then turn itself right side up at the last second, fire its engines, and try to land this thing. Remember, it's 16 stories tall. This is a big thing they're landing. Very tricky and dangerous. Well, we just had another test, folks, on Cinco de Mayo, and we have something to celebrate. There she comes. All 160 something feet tall of it. And she landed. They did it. This was not easy, and nothing like this has ever been done before. This is like a giant grain silo landing on the ground. It's incredible. And it's important too, because this isn't just a pie in the sky thing they're experimenting with. NASA has just declared that this vehicle is going to be used for something really important. These experimental tests are going to proceed through to about Starship number 20, prototype number 20. They're going to try to put that thing in orbit, in Earth orbit, on top of a giant booster that goes underneath it that's even bigger in this summer. They're saying July, it's probably August, September, something like that. But keep your eyes peeled. This is going to get really exciting. And Starship isn't just a project, it has a mission now. NASA has selected the Starship vehicle to be developed into a human lander. Now, they still want to use, in the picture there, you see with the 4 solar panels on it, that's the Orion spacecraft that NASA is building now, and they'll be testing it later this year. That is docked to a waiting Starship, which will be waiting in orbit around the moon. And then this monster is going to carry the crew down to the surface. And I do mean monster for scale here. Here's artwork to show what a landed Starship will look like. Direct your attention to the little things near the feet. One of those is a moon rover. Those are astronauts down there. This makes the lunar module from 1969 look like nothing. This is incredible. And now with this being selected, this makes the work that's going on down in Boca Chica, Texas, just that much more important. Fortunately, we had a big success, so we're on our way. As far as future things to look at, got a couple things coming up. Now, we mentioned that Chinese space station launch. The space station core is up there. In May, at some point, we don't have a date yet, a Chinese cargo mission will supply supplies to the station. They're doing that because you can see later, June, date to be determined, the Shenzhou 12 mission will launch a Chinese crew of astronauts. They're actually taikonauts, is what you say for the Chinese. 3 taikonauts to go and live on their new space station. Other space station business, we got the International Space Station receiving 2 resupply missions in June. At the beginning, SpaceX will launch an American vehicle to resupply the International Space Station. And in June, the Russians will launch their cargo vehicle to deliver more supplies to our very busy space station. Anyway, that gives you some idea of what's going on up there. And it's pretty busy and very exciting.
Yes, very busy times up there in space, down here on Earth to get things in space. I always like to remind people that money spent on space programs, the money spent here on Earth. People often complain, why are you spending so much in space? Well, we're not spending it in space. We're not going to the Jupiter Lounge and dropping money there. It's used here. People are paid here. The engineering is done here. The discoveries are made here. There's a lot of work that is done, has huge payoffs for industry, and a lot of the things that industry uses, NASA gives them for free. This research is just opened up and free for Americans to use. Now, in some of the most stunning research that's been going on in the last few years, it's been about black holes, in my opinion, and we often don't cover them nearly enough. Now, this is a simulation of what a black hole would look like as material orbits around it. The left-hand side's a little brighter as the material comes towards us. We saw an image much like this taken of the black hole in M87. But first of all, what is a black hole? Let me go through this very quickly. Imagine you're standing on Earth and you have a ball. You decide to throw the ball. You throw it up, it goes up, comes back down. That seems all normal so far. Now, what if you throw it a little harder? Well, it goes higher. Seems to make sense, comes back down. Now, what if you're really, really strong and you throw it really, really hard? So strong, you throw it and it doesn't come back. The question is, how fast do you need to throw it such that it does that? That's known as the escape velocity. That little VE, it is equal to actually this equation, the square root of 2 times g. G is just a gravitational constant. It doesn't changes. It's how strong gravity is. M is the mass of the thing you're standing on, and you divide all of that by the size of the object, or the radius, how far away you are from the center of it. Now, imagine, what if that escape velocity were the speed of light? What if you had to throw it so fast, you had to go the speed of light to get off the object? Well, nothing can go that fast. The rules of the universe, the way it works, that's sort of a speed limit. I'm not going to go into why that is the case, but if you now set the left-hand side equal to c and solve for the right-hand side, say r, you can figure out how small you'd have to make the Earth to make it a black hole. Now, I didn't calculate that. I'll leave that as an exercise for the viewer because we're running out of time here. But the Schwarzschild radius, that r, is equal to 2 times gm over c squared. It's quite simple, and that tells you how big that event horizon is. Now, the event horizon in reality is about that size for that image on the left-hand side of that M87 black hole. So that's what a black hole is. It's something that has so much mass in such a small radius that you need to travel the speed of light or faster to get away from it. And since you can't go that fast, you can't get out. Not even light can get out. So they're black. Now, the light we're seeing around this black hole actually is coming from the disk that's outside the black hole, the accretion disk. Material falls in, heats up, glows very brightly. And we're picking up that light. So we're not picking up light from inside that event horizon, but from just outside. And it does weird things. There's so much gravity there. The light wraps around several times. It's crazy. And folks did a simulation. It's that simulation we were showing at the opening that we flubbed a little bit. So we'll show you it again at the end, or we'll post it online for sure. But there were beautiful images from it. Here's a still, and you can see it's two black holes. One's bigger than the other. The blue one's the smaller black hole. They just color-coded them. They're not different colors because of the physics. It's just they made them that color, so they look good. But then they said, well, what happens if they interact? In fact, if you look at this one, let me use the laser pointer here just a little. There's some red light right along the very edge of this black hole. They zoomed in on it. That red light's coming from the other black hole. It has to go and make a 90-degree turn to get to us. So how crazy is that the light can do these things? It can bend it in this crazy way. The blue one is behind the red one now, so it would go forward backwards. So let me run a little clip of that movie, and you can see what these look like. So it should start here in just a second, I believe. Yeah, there they go. So here they're orbiting around each other, and everything seems kind of normal to us. And now we're going to see what would happen if you were viewing it from a different angle. So now that blue one's behind it. Now we're changing our angle again. So now we've gone off to the side. Everything's kind of normal. Well, normal. Why are those disks warped and weird? That's just the black holes. That's like a frisbee around a black hole. That's all it is. Well, more like an aerobie disk, really. But they aren't warped like that. That's gravity doing that warping. So crazy stuff when you have black holes. And we're able to simulate what it would look like to have two of them around it, what they look like from different angles, which physics has come a long way to be able to do these sorts of calculations. Another black hole story. This is M87 itself. This is the galaxy on our big picture. It's in the Virgo cluster. It's the biggest elliptical galaxy in the Virgo cluster. This is in the Gunther depths of space at Griffith Observatory. They've observed this galaxy and this black hole in many different wavelengths. Now, of course, we see visible light with our eyes, but there are gamma rays, X-rays, ultraviolet, the whole spectrum you can make observations in, and indeed they have. We also have an exhibit about the whole electromagnetic spectrum as well. It's currently turned off, as you can see. Griffith Observatory is still closed. We will let you know when we are able to have visitors again, but that's not right now, unfortunately. So this whole show's remote, and we're doing the best we can. The observatories that made these observations, a bunch of them in space, of course. There were some ground-based ones, too, involved on it, but you can see the ones there. And look at this. This is the list of observatories. And here's the little video they made. So those radio images, really sub-millimeter, to be able to see that black hole. And as you go out, you're starting to see some of the structure of the jet in the very closest regions within 1 light year of that black hole. The jet's caused as material falls into the black hole, heats up, and it's sent out on the poles in the polar directions of that accretion disk. And as you continue to observe in the radio, you're seeing more and more of the jet coming out of that black hole. So that's within about 100 light years. And now we're starting to look at the VLBI network, the very long baseline interferometer, and you're able to see these details in the radio. Now, other observatories kicking in. The Chandra X-ray Observatory, X-rays in this jet, visible light from Hubble, the Swift Observatory, New Star. So being able to observe across all these different wavelengths, seeing the highest energy to the lowest energy, the light, all created by this jet, but through different mechanisms. So we're able to piece this all together and really build a picture of how this jet works from the smallest scales out to some of the largest scales. So these are really unprecedented observations of these sorts of environments. And I can't wait to see these as they're taken over more and more years, to see if we can start to perceive changes within this. So moving along, we've also found a hidden population of high redshift double quasars. Now, that M87 galactic nucleus is active. It's shooting out a jet. And those sorts of things, depending on how you view them, can look like a quasar, which is a quasi-stellar radio object. They used to look like stars, and now we've learned they're black holes with stuff falling down into them. So some observatories were used, the Gaia Space Observatory, of course, the Longitudinal Sky Survey, Gemini, and the Hubble Space Telescope all took observations, and they discovered a population of these objects that kind of seem to strobe a little bit and flash back and forth strangely. They've learned that they have matter falling into them. They're probably interacting galaxies. You're seeing those. This, by the way, is an artist's conception. These are interacting cores, flinging out material. So these hungry black holes are getting fuel to glow like this brightly because of this interaction. Now let's see what the real observations look like. So this is what the scientists really saw. They were able to take some spectra, measure the flickering within the spectra, and see that these were actually flickering and eating material. Now, strangely enough, these are two different pairs of quasars. They're the same distance apart. We're not sure if that's a selection effect and their survey happens to be kind of tuned to pick up ones of that distance, but they're starting to pick up these double quasars, and this is new, and it's telling us about how galaxies are built, how they merge, and how these giant black holes might even merge together to get even bigger. Another result, this is the Centaurus A galaxy, known for that sort of distinctive S shape you see. I think this is a crazy looking galaxy. Well, it's a big elliptical that ate a spiral galaxy, we think, probably about 100 million years ago. When you look at it and add in some other wavelengths, you can add in X-rays and others, you see it also has a big jet shooting out from the center. That interaction caused material to fall down in there. The SOFIA Airborne Observatory was used to measure the polarization of that light. In other words, sort of the magnetic field angle of the light that's coming off it. It's not sort of, it exactly is what it is. And we're able to measure the magnetic fields within this galaxy and see if that merger had any effect upon the global magnetic field there. And indeed it did. You can notice, let me get out the little pointer to guide your eye. You can notice through here, the magnetic fields are kind of coming up, and then they go across, and then they go upwards. So there does seem to be a global structure and sort of a bending in the magnetic field that we wouldn't necessarily expect to see. That's because you had two galaxies. One fell into another one, and they probably each had their own magnetic field, and now they're interacting, creating a global new magnetic field for this object. So these sorts of observations from SOFIA let us probe this for the first time and really take a look at what it's like. Now, we've got a new section of the show to dive into here. Inquiries from the foundation. We decided that we would let our foundation members ask a question, and they were offered that chance, and David Press offered a couple of questions, great ones to us, and he wanted to know, first of all, and he is a foundation member. Thank you so much for your membership, and thank you to all foundation members out there that help us create the program that we do, help give us what we need to help do all this work. So anyway, and we have a donate button down there, by the way, if you feel like clicking it and you haven't donated. Those that have, we thank you. I sometimes forget to thank the people that are donating. It all helps us run our school program. But anyway, back to the inquiries from the foundation. He wanted to know, what has the space station been up to? What experiments have been happening? And how are they benefiting humanity? So just a small question from the foundation to kick off this new one. And if you have a question in mind and you want to send it in, join our foundation and you can send in a question. Maybe we'll pick it next month. But I turn this over to Brendan. Brendan, are you out there? There you are. So what did you find that's been going on the space station?
Well, some interesting little updates from one of humanity's most remote laboratories, which would be the International Space Station, all the way out there. I did some research, found out that there are some 2,000 odd experiments that have been happening on the space station. And of course, a lot of them are really nitty gritty, kind of minute things, but all of them are impacting us in some way, one way or another. Some, of course, more so than others. And I'd love to talk about some of them. So if we go to the next slide here, the first thing that comes to mind for me when I think of work that's being done on the space station is, if we go to the next one, sorry, I don't have access to the things, is access to water filtration. Of course, resource conservation on the International Space Station is incredibly important. The astronauts there, I mean, sending anything up into space is really expensive, and people who are living out in space are going to need water and food, all these things. One of the things that's done is filtering things like sweat and urine that the astronauts are producing and turning it into clean drinking water. And so here you see a picture, this is a picture that NASA took of them using some of that water filtration out in the real world in places where getting access to clean water is difficult. So for me, that's kind of like the main, oh, of course, clean water is huge. There are tons of other things that they're doing as well. If we go to the next, there are plenty of things happening as far as medicine and medical research. Things like different viruses or bacteria happen to grow a lot faster and mutate more rapidly out in space. So doing experiments on diseases is something that's pretty common up there, as well as growing proteins. You'll see this image of a purple protein structure. On the left side of that image is how a protein might form on Earth, but without any gravity impacting it, the protein can form a lot stronger. So a lot of things about growing proteins for different medicine. And you'll see Cosmonaut Shapirov getting an ultrasound done around his eye, looking at the bone around his eye. And so things like that, just out in the field, kind of ultrasounds to do medical tests are things that they're developing and reaching out on the International Space Station. Let's go to the next slide. There's plenty of other stuff too. There's lots of stuff with food, as I said, resource conservation, incredibly important. So here you'll see astronauts Walker and Hopkins. Astronaut Walker is working on some growing bacteria and other very high nutrition density foods that can be eaten and stored out in space that are, high calorie and nutritional value with very low mass and other things like that. And then astronaut Hopkins over there is looking at some plants. They're growing plants, of course, so they can see if you can grow plants in space, but also the way to distribute water to the roots of all of these plants, because there's no gravity, there's no water that's naturally, in soil here. Things that are important in places where food is scarce or where water is scarce. Doing farming out in the desert where it might be hard to irrigate your crops. This is research that's being done to look into that as well. If we go to the next slide, you can also, there are a lot of industrial impacts. 3D printing has been developed in space to make sure that the 3D printers are working incredibly well. They're printing without gravity. Those have been affecting us here. I have a 3D printer in my closet, actually. It's running right now. And that has been influenced by the International Space Station. And then growth of things such as crystals. Those happen to grow without the influences of gravity. So for a lot of industrial purposes, more technical than I understand, but growing crystals is something that's also being done and is impacting our understanding of how those things grow. There are a ton of other little odds and ends too. We're studying biology and things like fruit flies by having them live up, being born and living their entire lives out without any gravity or the radiation of space. Colloids, which are, they're materials suspended in a fluid substance. So things like skin creams, those sort of things are being tested up there. And even just transitions from states of matter are being inspected in fine detail. And even the stuff that you'd think, no, there's no way the International Space Station, well, if we go to the next slide, even something like soccer, there's actually an experiment being done right now with a soccer ball up on the International Space Station, where they're checking to see the impacts of a free-flying object in its environment around it. So even something like a soccer ball, they're testing and they're trying to learn more about the physics of a sport like soccer. And of course, things where our eyes to the future of being out in space, everything that they're doing is so we can know if we're going to be able to live out in space, what food we can eat, what sort of things we can bring, what we can make out there, all of those things. So there's just tons of stuff on the International Space Station.
I lose Brendan too. I think it's a thing on this Friday night. But Brendan, thank you for that report. It's absolutely true. If we want to live out in space, we need to learn how to do it. The International Space Station has really been our first our first real attempts to do a lot of this stuff. So thank you, David Press, for that inquiry from the foundation. If you want to have one, you too can join the foundation and do that. Also, don't forget, we had some guests. My advisor, Raja, and his wife, Mila, joined us. I forget what year that was. This last year feels like it was about 14 or 15 of them. But back on our YouTube channel, you can go find the show where Mila talks about her research on fruit flies and the health of them and what it happens to them up in space. So all that could happen to us too. So very important research that's going on.
I'll drop a link to that in the
Thanks
chat.
to the foundation for all you do out there. And I think we lost Brendan's audio, so we're just going to move on here. So Patrick, how about you tell us what's going on out in space for our Sky Report? And thank you, Brendan, for the report up until the time we lost you, at least. It's that kind of night, folks.
Yeah, I just want to mention that.
Uh-oh, Patrick, are you muted?
Not again.
Oh, can you hear me? Can you hear me?
Yes.
Okay, well, what a night for technical glitches here. So anyway, okay, well, what's in our skies tonight? And I just want to kind of bookend the International Space Station. Occasionally it can be seen over the skies of Los Angeles as a brilliant star, almost as bright as Venus when conditions are right. All right, so if you were to go out in the mornings, say about 4 a.m., what can you see? Well, what you can see, if you look to the southeast, are two of our largest planets in the solar system, the brightest of which is Jupiter, and the other planet is Saturn. That's over in the southeast in our morning skies. The constellations and stars that you would normally see in the summer are present, such as Scorpius with its bright star Antares, and there are other constellations that are present. Now, something that you can't see from the city just because of the bright lights is something that sweeps down from the constellation of Aquila and down between Sagittarius and Scorpius, and that is the Milky Way. So if we could take the same sky view from an area devoid of city lights, far from city lights, we'll see a sky that looks like this. And it is incredibly beautiful. Here we can see the full extent of the Milky Way and the brightest portions, which is positioned between Sagittarius and Scorpius. And out in the Joshua Tree, Anthony Perkic took this beautiful photograph of that region in Sagittarius and Scorpius in this time-lapse image. Now, moving on to our evening sky, there is a chance to see the brightest planet in our night sky, and that is Venus on the 12th, just right after sunset. The moon is positioned right by it. It's only 1.5 days old, so it's a very thin crescent, so it makes for a beautiful view if you go out that evening. The moon does move in its orbit around the Earth, and so just before we do that, the moon is roughly about 1.5 degrees from Venus, and the next day it is just close to the elusive planet Mercury, which is often hard to see, but here's a good chance to see the moon and Mercury in the evening sky. Then a few days later, the moon makes its way and is next to the planet Mars, roughly about 1.5 degrees. In the constellation of Gemini, the twins, its brightest stars are Castor and Pollux. So that's something to watch out for. Now, just in general, our evening sky contains many interesting constellations, and you can go out, stargaze, look towards the south, and look for constellations such as, get my laser pointer here, there's, over here is Leodolline with its bright star Regulus, and the constellation of Virgo the Maiden. A little bit more challenging is right below Virgo the Maiden are these 4 stars that make up Corvus the Crow. You can try your hand at that. And then over, okay, and those are some of the things you can see in the evening. The next thing we have is our moon phase chart, and just going through the moon phases here. And okay, last quarter is on the 3rd, and we have new on the 11th, and on the 19th is first quarter, and then there's the full moon, which corresponds to a total lunar eclipse on the 26th of this month. So this is the first time we've had a lunar eclipse since 2019, which will be visible here in the West Coast and Western United States. So what happens in a lunar eclipse? Well, the moon moves through the shadow of the Earth and is darkened just briefly. The side that's facing the moon that is a side where you can see the entire eclipse. And if we look at a map here, the lighter parts of this map is where the eclipse is visible. So Australia, Southeast Asia, and western parts of America, and also South America, where the eclipse is visible. Here here in Los Angeles, these lines that you see here represent where the moon is on the horizon at various phases of the eclipse. The Earth casts two shadows into space. The darker innermost shadow is called the umbra, and the lighter part is called the penumbra. And if we put this into a diagram showing the shadow projected in the sky, we see the umbra and the penumbra. So this is the scenario for the 26th at 1:48 a.m. The moon just touches the penumbra and is not. It's still a full moon and nothing happens. And then it darkens on the left edge as it moves into the umbra at 2:45. At 4:11, it's completely immersed in the Earth's umbra, and it kind of turns red, which means that it kind of is taking all the light of the Earth's sunrises and sunsets, which is what we're seeing there. And then mid-eclipse is at 4:19, and then exits at 4:26. This totality phase lasts only 14 minutes, and that's because the Earth skirts the northernmost part of the Earth's umbra. And then it's out by 5:52, and then a minute later, the moon sets here in Los Angeles, but the sun will already have risen, so it's in daytime. The eclipse concludes at 6:50 if you're out in the Pacific Ocean, but the moon here in Los Angeles will be below the horizon. Here's a summary of all the phases of the eclipse that night. And we also have a little animation of what it would look like. The moon is in Scorpius, and we'll go ahead and play that animation.
Back it up too and run it again, Patrick.
Yeah, I'm not sure what happened there.
Gremlins.
There we go.
Oh, yeah, there it comes.
Now notice that the full moon, when it's in eclipse, is dark, and the sky becomes dark enough to see fainter stars. And here's where we come into the sunrise portion. Then the moon is gone. All right, so that's how you can see the eclipse from Southern California, but we actually are going to stream it. The All Space team will be at the observatory, ready to bring this eclipse for our audience here, and in fact, our worldwide audience. And to find it, go to our YouTube page and look up our link there. And this is the total eclipse page. So if you don't get to see it, we'll certainly be there to document this eclipse. So it's going to be a really great night for us, assuming the weather is clear. There's the QR code. Just scan it with your phone, and you can get to our eclipse live streaming site.
Yeah, thank you, Patrick, for that wonderful sky report. And I hope everybody's taking these warmer nights, but before they get too short, as an opportunity to go out there and do some observing. And I hope you all join us later this month for the total lunar eclipse. We'll be bringing it to you live. It's going to be a lot of fun. Now, Katie, are you out there? It's time for some pretty pictures. with Katie. And also, you're going to give us a space weather report too, I think, going forward now. So I'm looking forward to that. Let's hear what we have.
So here we have a beautiful image. This one's called Hubble Revisits the Veil Nebula. Another gorgeous Hubble image. This is Hubble takes a spiral snapshot. And the following images are a series from Anthony Perkic, taken from Joshua Tree on April 9. This is the summer Milky Way over Joshua Tree. And the galaxy M100. Another beautiful galaxy. This is M64. And a gorgeous image of bright star Antares. And this is a sun halo right as a raven flew past over the Samuel Ocean Planetarium. And the last of Anthony's, this is April's full moon. Here is the moon on April 17th. This one's by David Pinsky. And finally, to some space weather. So these are some gorgeous videos of the sun from NOAA, which showed the sun's current activity. And on the left, you'll see the solar extreme ultraviolet. On the right is the current coronal mass ejections. So NOAA uses this information to create an aurora forecast, and you'll see most of the forecast is bright green right now, which represents a low probability of aurora or northern lights being seen. So on the lower left there, you can see the probability percentages.
So now those two things are connected. When you have coronal mass ejections, you can get more aurora, and I wasn't seeing a lot of coronal mass ejections. Is that correct, Katie?
Yes, that is correct. There were not a lot. There was a little bigger one yesterday, but if you go to the NOAA website, they update it daily. So you might be able to see more if you go tomorrow or the next day. So speaking of northern lights, here we have a gorgeous image of the northern lights. This is over New Zealand. This was taken by SOFIA, which is also known as the Stratospheric Observatory for Infrared Astronomy. So recently, NASA released a story about SOFIA being able to collect data from the Earth's atmosphere. About a decade ago, a team led by German researcher Heinz Ubers improved the infrared telescope called the German Receiver for Astronomy at terahertz frequencies, or GREAT. And this allowed them to study Earth's atmosphere. So SOFIA collected data from our atmosphere, and that resulted in a study published by Nature Communications Earth and Environment, stating that GREAT was able to directly measure oxygen in the lower atmosphere and mesosphere. So this is from NASA. These results will help our understanding of the science of how solar energy is exchanged between the surface and space, and will also help researchers learn more about Earth's atmosphere in the future.
Well, that is fascinating stuff. Let me make sure I'm unmuted here. I was talking to our audience, by the way, in the chat. Sorry about that, getting distracted as I'm having fun out there. But anyway, thank you, Katie, for that. SOFIA, by the way, folks used to kind of make not fun of it, but we're wondering, what's it going to be used for? How is it going to be used? You're building this big 747 with a hole cut in the side, and we have infrared observatories in space. But every year, it seems like they're showing more and more capabilities. SOFIA's really been a great instrument, and now it's being used to study our atmosphere. So absolutely fascinating. So thank you, Katie. We'll see you again next month with more pretty pictures and more space weather. And now it is time to turn to our guest. I'm very happy to have join us Natalia Guerrero to talk about worlds beyond our own, new discoveries from NASA's Tess mission here at All Space Considered. So first of all, welcome, Natalia. So welcome to have you here, and thank you for hanging in here with us. As is our style, we are running late again tonight, folks, so we're going to go well beyond 9 o'clock because we're going to give you a chance to hear from Natalia. You are the Object of Interest Manager at MIT. You're at the MIT Kavli Institute there, working with Tess, and that means you get to deal with sort of all of those objects that Tess is observing and figure out which of them could be exoplanets or might be candidates for it. So you're the one that has your finger right on that pulse. In addition, he just published a paper that had like 100 authors on it. It was crazy long. And it was literally the first release of saying, hey, here are these candidates. And it wasn't just one or two. I'm not going to tell the number. I'm going to let you tell that because it'll be fun. But I do want to say we prepared something special for you here at All Space Considered, just to show what we think is could be used to sort of inspire you out on your mission. We built you a hovercraft, the Exoplanet Explorer hovercraft, and you're out there. It's you versus the biggest problem in the world, and you're solving it there out in space with the Tess mission, and you're getting it done. So I hope you're pleased by what we've done for you here at All Space Considered. So, ladies and gentlemen, welcome. Natalia, take it away. It's all you from here on out, and we'll ask some questions once you're done.
I love it. Oh my gosh, this is amazing. Oh, I can see. Oh, this is really great. I love this.
Well, we are happy to send you a copy, and there is a story behind that, but I'll let you all figure it out on your own.
Oh my goodness, this is great. Yeah, so thank you so much for hosting me. I am part of the Tess Science Office at MIT in Cambridge, and got my laser pointer going. So I work here. This is the campus of MIT in Cambridge, Massachusetts. And more specifically, I work here in this office that has a really nice view of MIT's dome. And I work in the MIT Kavli Institute for Astrophysics, but specifically on the Tess mission. So Tess studies something called exoplanets. So exoplanets are planets that are outside our solar system. So we have the 8, not 9, planets in our own solar system, but we now know of thousands of exoplanets outside of ours. And so this is really exciting because we didn't know about this 30 years ago. This is something that has happened in just the last several decades. And so why is this important? Why do we care? If we look at our own solar system, we can start to try to put together a pattern. We have a handful of small rocky planets towards the inside, close to our host star. And then as we move further out, we see that we have gas giants, Jupiter, Saturn. And then as we move further out, we also have ice giants. And then as we get even further out, we have these low brightness, rocky objects again. So we have this configuration and we know what kind of star our sun is, but we know that there's billions of stars in our galaxy, and a lot of them are much larger than our sun or much smaller, different temperatures, different clustering, different ages. So there must be a different, or maybe similar. There's a lot of questions about how do systems form of exoplanets? So that's one question that we're trying to answer by studying exoplanets. Another, for folks who care a little bit more about what's under our feet, is how unique is Earth? So we have all of these amazing spacecraft that we've talked about tonight that are all trained on Earth, trying to understand our atmosphere, our interactions with coronal mass ejections. And Earth is really a special place to live. We have water, we have land, we have a magnetic field, and we have, I really like this picture. This was actually taken from one of the Apollo missions. We have this really beautiful thin, very, very thin, but very critical atmosphere that has clouds and water, oxygen, all of the critical things that we need for life. And we know because we live here, that Earth is a really special place to be. But what about all of these other exoplanets that we're now discovering? What are they like? What is their story? How did they form? And this leads me to, I think, the question that stirs the most imagination and creativity. Are we alone? Is there another planet like Earth, another system that looks just like our solar system? And what does the search for life look like? Are we looking for an atmosphere that looks like ours? Is this something completely different? So this question of are we alone, I think, pulls at my heartstrings for sure. And I think it it really does motivate the study for planets around other stars. So what have we done to actually find these planets? So back in 2009, the paradigm of studying exoplanets really took off and accelerated. Before this space telescope Kepler, which was shown here in the foreground, before about 2009 when it launched, we knew of maybe a few hundred exoplanets that had been discovered by some previous space-based telescopes, but also ground-based telescopes at observatories all over the world. But then with Kepler stared kind of like a pencil beam at one tiny patch of sky and said, okay, I'm going to look here and I'm going to try and count up all of the exoplanets in this patch and do a census. And Kepler found thousands. And from those thousands, we were able to extrapolate something really fundamental. The exoplanets are common. They're commonplace. And that means that for the billions of stars in our galaxy, there's likely billions of exoplanets. And this is a really huge takeaway that Kepler gave us, that we are surrounded by this exoplanetary family. And since then, we've been able to devote many more resources to characterizing exoplanets to try and find out where in this family tree Earth belongs. We found that there are planets that we've been able to match up to the ones in our own solar system, but there's also planets that look nothing like Earth. So there's super Earths that are maybe 1.5 to 2 times the size of Earth or a little bit smaller. There's also a really unique type of planet that we haven't been able to find in our own solar system, mini Neptunes that are smaller than Neptune. Neptune is about 4 times the size of Earth for reference, and giant planets, planets that are even bigger than Jupiter. And so we are starting to figure this out. And also we've been able to look at protoplanetary disks, the big sort of hula hoop tutu of matter that is surrounding stars. And that's what planets pull themselves together from. And so we're starting to figure out where we've come from, where we're going. And I work on this really amazing little spacecraft called Tess that has been able to continue this search. And how does Tess do it? So Tess is a mission that uses the transit method. So it uses the same method that Kepler does. We're not directly taking a picture of the exoplanet because the star is thousands of times brighter. It's so much brighter. But what Tess does is it's able to measure the amount of light blocked by the planet as it transits or crosses in front of the star. So a big planet will make a big transit, and a small planet will make a small dip. So that's what's shown in this light curve, this plot of brightness over time. And so we're able to back out from that the planet's relative size compared to its star and how close it is to its host star. So if we know about the star's temperature, we're able to figure out about how much radiation, how much energy is reaching the planet, and we can start making rough estimates as to whether or not the planet is in the habitable zone of its host star, meaning whether or not it's able to sustain liquid water on its surface. So here I have a schematic of a theoretical exoplanet system with a bunch of planets orbiting its host star. And so as we launch this into motion, we can see that some of these planets are in its habitable zone. They're able to sustain liquid water on their surface. And then some of them are too far out. You may have also heard of this as the Goldilocks zone. And for similar reasons, like the story said, some are too hot and some are too cold and some are just right. And so Tess has actually been able to find a planet in the habitable zone. Early in 2020, Tess found a new exoplanet called TOI 700d, which is not really a super memorable name. And there we go. It is part of a 3-planet system. This was around a small reddish star, smaller than our Earth. And the planet is about 1.2 times the size of Earth. And it's right here at the very inner edge of the habitable zone for this host star. And its period is less than 40 days. So its year happens a little over 1.5 times a month. So imagine that, having a birthday that often. be a lot of birthday cake. So this is just one example of a system that Tess has been able to give us this picture of, that we've been able to go after with ground-based telescopes and also with space-based telescopes like Spitzer, for example, before Spitzer retired. So, but let me give you also the big picture of what Tess has been doing. So Tess has been mapping the sky over the course of 2 years. First, it started on the southern hemisphere, and then it flipped over after a year and looked at the northern hemisphere. And so it looked at each one of these sections for about 27 days each, and it has been filling this in. Once we did this in our first 2 years, we launched in 2018. We've gone back and looked at the southern hemisphere again. We're almost done with that. So at the end of June, we're going to be turning back around and looking at the northern hemisphere. And this is really exciting because whereas Kepler, I said, was really focused on just one patch of sky, Tess is looking at the whole sky and trying to find where are there exoplanets around bright stars that are relatively nearby, and where are can we find small exoplanets around those stars? So let me give you a little picture of what we've actually found in comparison to what we already knew from Kepler. So here I've shown our Tess map of all of the sky that we've managed to image with Tess. And on top of it, I've shown in these yellow dots all of the transiting planets from other surveys. The big blob here at the top, let me pull out my handy laser pointer. Up here, this is all found by the Kepler mission. And then these sort of clusters here are the different campaigns, the fields looked at by K2. So thousands of planets pulled out of this mission and other missions like it. And then I'm gonna wipe those off the board and just draw the Tess planet candidates on there. So we've been able to cover the whole sky by going section by section, sector by sector. And in 3 years, we've been able to find over 2,500 planet candidates. And as we continue to look both at the southern sky and at the northern sky, we're going to try and fill in some of these gaps and also look along the ecliptic. So we'll be overlapping the Kepler field and the K2 field, which I'm really excited about. And we're going to be adding to the number of exoplanets we know. And in my head, this ends up being like a to-do list to me, because there's all of these individual planets that have their own story, and then they all belong to a larger population of planets. And then we're putting together this huge family tree like that picture I showed at the beginning. So there's a lot of work to do. It's really exciting. There's a lot of new people coming on board. It's a rapidly growing community, and I'm really excited to see what Tess does next.
Well, that is some amazing, amazing stuff you've got going on there. Now, you said there's over 2,500, 2,600 candidates so far, but your paper only had whatever 2,200. Are you breaking news here live at All Things Considered, announcing that there's another few hundred that are going to be coming soon?
Yes, so Tess, actually, the catalog of planet candidates is alive, and we're always adding candidates to it. So we host this publicly online in a number of places. One is actually not that far down the street from the observatory, or maybe it is, depending on traffic, but the Caltech IPAC hosts the Exoplanet Archive and the follow-up program there. So that's one of the places where our catalog appears. And so we actually go through with a team of people, and once the data has passed through our pipelines and our analysis and a bunch of filters, we look at the top couple hundred candidates or so from each new data set with a team of really amazing people. And we say, okay, these are the ones that we think are planet candidates. And so basically once or twice a week, we'll release half a dozen new candidates. And those are picked up immediately by telescopes all around the world. And a whole team of follow-up observers leaps into action and goes and observes those and starts the process of discovering new planets.
Well, that's just awesome. We've been covering exoplanets here at All Space Considered really the whole time we've been doing it. It's some of my favorite stuff, but to hear it from you, someone that's doing it on the ground, have your hands in the research is just great fun. In fact, our crowd over at our YouTube chat have been asking some questions. One person wanted to know, are there anything new with the Trappist system? And is the Trappist system going to be one of the ones you'll be able to observe? Do you have any news on it?
So that's a good question. Trappist is around, I think it's around, it orbits an M-type star. And so Tess is really, its cameras are sensitive to the redder wavelength. So we're really excited about M-type stars. And often the planets around those stars, if they're close in and small, it's a lot easier for us to detect because small planet, small star, but the dip is big. So
yeah, for the folks that don't know, the Trappist system has 7 candidates, and I think 4 of them are within the habitable zone. So it's a super interesting system that we've reported on before at Allspace. But it sounds like you don't have any data to tell us about just yet, but Tess is designed to look at exactly that type of star, though.
Exactly.
So that's amazing. Another question we had, someone wanted to know what percentage of the sky will be covered by the end of the second pass, but I really think you're on to year 3. But you said you're going to fill in almost all of it, but that chunk of the galactic center, that's the big block over there that you're not going to look at. Are you not going to observe there, or will that also be filled in eventually?
So we are going to cover that. We're going to cover up part of that. I think I have a picture that shows where that's going to show up. But we're going to go from having covered 70% of the night sky to 88% of the night sky.
Yeah. Okay, just fascinating. Now, keep in mind, everybody, that this is not as deep of a survey. Kepler stared at one patch a very, very long time. So Tess is designed to pick up exoplanets that would be around nearby stars. It's going to look at almost all of them within all these patches. So it's super exciting to sort of get a distance limited sample. It really lets you see what the truth is out there. So this is just a wonderful mission. It adds to our knowledge of what Kepler does. So what are we seeing here? This is one you've brought up.
Yes, so we have the year 1 and year 2 Tess image underneath, and then you can see that our third year has basically tried to reobserve and fill in some of the little tiny gaps in our first year of observation down here in the south. But then in the north, what I was talking about before is we're going to go back to some of our northern sectors. We're going to try and fill in some of these gaps. We weren't able to observe those initially, and again are going to be challenged by scattered light from the Earth that contaminates the test cameras and makes it hard to get good photometry, good measurements of the brightness of stars. But then we're going to turn Tess on its side and look at the ecliptic plane, and we're going to be able to see some of the Kepler, the K2 campaigns there. So I'm really excited for those because there's going to be a lot of stars in those cameras.
Yeah, I was going to say, what in particular are you excited about? Comparing how the two look, or what about using the 2 data sets together excites you?
I'm really interested in seeing, it's been really great seeing planets that we saw the first time around, a second time around, and checking in with them 2 years later. It's like a celebrity is like, where are they now? And because we're able to get a better idea of how often they go around their host star, we're able to measure them more precisely. But especially with the ecliptic, it's going to be about not only exoplanets, but also there's just so much happening in the ecliptic plane. And one of the things that Tess has actually been really good for, and that's emerging from Tess, is being able to find asteroid tracks. I don't know if you knew about this.
No.
Tell us about asteroid tracks.
Yeah, so asteroids are kind of bright, especially if you stack a bunch of images together, they just pop out. But you can see them move from image to image because Tess takes images every 10 minutes right now in the extended mission. So in year 4, you're going to have basically a 10-minute time lapse, essentially, of like one frame every 10 minutes for a month. And so you can track an asteroid that way and figure out its velocity and things. And there's so many in the ecliptic. So this could be a great data set for teams that are interested in asteroids, in confirming asteroids found by other spacecraft like NEOWISE. So I think that's one of my favorite things, is that Tess is really amazing for exoplanets, but it's also this really powerful tool for all sorts of other astronomy and astrophysics.
Mm-hmm. In fact, that was one of our questions. Can you characterize briefly, this was from Carolyn Collins Peterson, can you characterize briefly the non-exoplanet objects Tess has seen? I know that it's seen some supernovae, but anything else? And what about those supernovae it's finding?
I can talk about, we've also been able to observe a tidal disruption event. Trying to remember the name. I think it was called Assassin 19KO, but essentially it's this massive star that is going around the center of its galaxy, and the center is a black hole. And so every time it whips around, the galaxy snatches a bite of the outer shell of this giant star. And that creates all this energy, and some of that is given off as this huge flare of light that we can measure from here on Earth, and you can measure other things in other wavelengths, but Tess is interested in the light. And because this is an orbit, it's predictable. And so this was known about, and we realized, oh, hey, we're going to be able to observe this with Tess. And so Tess was able to contribute a really high quality light curve to the multi-wavelength data set for this tidal disruption event. It was really cool.
Yeah, that's super interesting. Tad Daly wants to know, I hope I'm pronouncing that right, Tad. If Tess were at the right location, would it be able to see planets orbiting our own sun? You want to know if it would see 9 objects, and I think that would be unlikely, Tad, only because Pluto's orbit's quite tilted, and Pluto's really, really, really small, so it's not going to block out much light at all. You'd see our moon long before you'd see Pluto, but would you be able to see planets around our own sun if you were in the right location with a spacecraft like Tess?
Yes, that's a really good question. So Tess is always pointed away from the sun, and it's orbiting the Earth, and it's trying to balance, its orbit is balanced with, it's in resonance with the moon. And so we've actually gotten a little bit of Mars in the field of view of Tess. We weren't planning on that, but it ended up being a really good test of Mars is super bright in the Tess cameras. And so that was, yes, like you don't want Mars in, we're trying to avoid planets.
Well, I think Tad wanted to know, say if an alien civilization, say on Proxima Centauri, were looking back at our own sun, and if it were in the ecliptic, I don't think Proxima Centauri is in the ecliptic. So anyway, a star in the ecliptic. Chris, you probably know which stars are in the ecliptic better than I do, or Patrick.
Sure.
Pollux is in the ecliptic?
Close.
Close. Anyway, so a star in the ecliptic, so would be looking back towards the sun, and our own planets would transit from that view, perhaps. Would Tess be able to see that from a nearby star?
We'd have to get pretty lucky.
Okay, so not all stars are gonna, you have to planets. The orientation has to be just so. But if it were just so, I think Tess could see Earth and probably, I would guess, Venus, Earth, certainly Jupiter, certainly Saturn, Neptune, Uranus. But again, you got to get lucky. They have to cross. So most of the time, the object's just going to go around the star, and Tess is going to be blind to it. You need other techniques. So it's some small fraction. It's a few percent of the stars have that orientation just right. But anyway, that's another story. Let's see what else that we have here from our folks. Have we seen a planet like Hoth? So sort of from the Star Wars universe, the frozen planet of Hoth from Empire Strikes Back. Are there any frozen worlds out there, you think, that are on the far edge of the habitable zone that we've seen?
I can't think of any right off the bat, but I know we have found some that are too cold. And Kepler definitely did, because I think there's a lot of Star Wars references that have been flying around since May the 4th. So,
of course.
But yes, that's like one of the other interesting things is, what about the too cold planets? And I think we have found some of those with Tess as well.
Yeah, I think so too. Now, any signs of any exomoons? I'm not sure what our luck has been, even in the Kepler sample. And I thought we might pick some up, but my guess is down in the noise, they get lost. But
yeah, there's been a couple of papers on like what the sensitivity would be required and like what the signal would look like, but we haven't had any 100% definite exomoon detections yet.
Well, that'll be an exciting day when we get to see those. So what's next for you that you're excited about in the exoplanet realm? I know you want to see this data comparing to Kepler, but beyond Tess, are there any missions out on the horizon? Any other instruments coming online that you're interested in?
Yes, always. I'm really excited because Tess has been kind of the scout mission trying to find small exoplanets around bright stars that other telescopes can look at. And one of the telescopes that we're interested in is the James Webb Space Telescope, which will hopefully be launching at the end of this year. And one of the reasons why is because planets that Tess finds that we then measure the mass for, we can start making some stabs in the dark as to the density of the planet. And we want to then understand, okay, if this planet has an atmosphere, what is in that atmosphere? Because we know our atmosphere is super complicated and there's clouds, there's weather, there's ions floating around. What does an atmosphere in another exoplanet look like? And one of the many tools that James Webb is going to have is going to be an amazing ability to measure the light passing from a star through its planet atmosphere and reaching the telescope and give us that chemical fingerprint of that exoplanet's atmosphere. And we'll be able to start piecing together, does it have nitrogen? Does it have carbon dioxide? What's there? And we can look at that in much better detail than we have been in the past.
Wow. Well, thank you for that. That is super exciting. Fingers crossed about Webb getting up into orbit. It's been taking a really long time to launch it, but of course, we want to get it right. It's not going to a location. It can be serviced, folks. So it's not like Hubble. Hubble, they made a mistake. They were able to fix it. This has to work correctly. We were lucky to go down and view it. Griffith Observatory, we have some folks and friends that work down there. Our foundation was allowed some folks and got to see it in person. It was pretty impressive. It's much bigger than you think it is. People working around with straps, holding cell phones out, taking pictures, and you think, oh, don't drop the cell phone. It's just, but anyway, when it's up there, it's going to be amazing. And indeed, a lot of the targets Tess is finding, we're going to be able to sample those atmospheres and make measurements. And we're living in really a new time here with, when I entered graduate school, we didn't know about very many exoplanets. One, it's showing that I'm getting old, but two, it's showing the rapid rate at which we are discovering these exoplanets and the pace at which we are moving forward on this. So thank you so much for joining us tonight, Natalia. Thank you for our audience out there with all your great questions. Once again, I want to thank Patrick for joining us tonight, Patrick. So Chris Butler. I want to thank Brendan for doing the wonderful work, doing the research on the ISS. I want to thank Katie for the pretty pictures. Oh gosh, I want to thank Angelica for joining us with the wonderful in memoriam of Michael Collins, and our entire crew that does all the hard work. Hannah, for your beginning work. I'm going to try and click us back to the beginning opening, so don't get too confused. We're not actually reopening the show here. I'm just going to run that opening video for everybody, or maybe Matthew. Oh no, there it is. I think I can actually do this. So here we are back on here, and I'm going to run the video, and we'll end on the video after that. But I do want to say, All Space Considered is produced by Griffith Observatory, which we are from the Department of Recreation and Parks in the city of LA, funded by the city. Our foundation helps us. It's our nonprofit partner in a lot of things we do, like our school program and other things like that. So thank you to the foundation. Thank you to foundation members. And thank you to our guests one more time. Wonderful segment, Natalia. Fantastic hearing about Tess. And thank you to our audience. No, you're very welcome. And we'll be happy to send you a copy of that image we made, and you can show it off to your friends. Make your dreams come true. No, anything. It's so fantastic to have you here hearing about all these candidates. And to our audience, we'll be back next month and sending your questions to the foundation members. And we'll be back with more All Space Considered on the first Friday of the month next month. Thank you, everybody. Good night.
Good night.
Night.
So let's run the video.